Okay, welcome everyone to the Astronomical Society of Edinburgh, wherever you happen to be in the world. Hope you enjoy our meeting this evening. This is what we've got coming up. My name is Mark Phillips. I'm the president of the society, and I've just got a couple of slides about what's coming up, what talks are coming up over in the next few months. But the main event of the evening that you're all here for is to hear Dr. Jason Wang, who's with us from Chicago, telling us about real images of exoplanets. So that should be really interesting. Looking forward to that. We have our members on Zoom, and we have visitors from all over the world on YouTube as well. So if you have any questions, and we'll leave them to the end, and we'll call them out at the end, and hopefully Jason will have time to answer those. Okay, so this is what we've got coming up over the next couple of months. Our next meeting on the 7th of February. This will be a hybrid meeting, so we'll be live in Edinburgh at the Augustine United Church. And we'll be on Zoom for members and on YouTube for visitors, and that's about the European Extremely Large Telescope from Dr. Stuart McKechnie. On the 12th of February, we have our Imaging and Observing Group meeting. That's for our members only, and that will be online as well. That's for members, that's a really good place to learn about astronomy where we all learn together. And if you haven't been to one before, then definitely worth coming along to that. On the 21st of February, an online only meeting with John Mowat telling us about the first Chilean observatory, not John Mowat, Dr. Daniel Bustamante telling us about John Mowat and the first Chilean observatory. And that will be on Zoom and YouTube. And another hybrid meeting on the 7th of March will be shedding light on the dark side of the universe with gravitational lensing, and that's Dr. Ben Giblin as well. The 4th of April, for our members, we have a members' night. Visitors are welcome to come along to that, but we're looking for some short talks from our members. So if you wouldn't mind getting in touch and give me your ideas of what you'd like to speak about, we'll have probably space for maybe half a dozen short 10-minute talks. So let me know if you've got something you'd like to speak about, and we'll sort that out. But that is really it from me. I'm going to stop sharing. Jason, if I can hand over to you. And this is what we're here to listen to. So thank you, Jason. Over to you.
All right, thanks, Mark, and thanks everyone for inviting me and having me here. Happy to talk with you about what I work on and hopefully show you some cool real images of exoplanets. Just double check my slides look okay?
They look good. Thank you. Yes. Thank you.
All right, so let's begin. Yeah, so I'm going to talk to you all today about how we actually take real images of exoplanets. None of that artist conception stuff that you might see in some of those popular science articles. So our main challenge here is we're trying to image planetary systems. You know, planetary systems can have planets. They can have asteroids like our own asteroid belt and Kuiper belt. But the challenge here is that there's always a bright star in the middle, and how do we see images of all these faint things next to the glare of their bright stars? So we're going to go from these cartoons that these are some. I'll show you some cartoons that I drew back when I was in graduate school and had enough free time to draw cartoons of these planetary systems and go from there to real images. Okay, so you all probably are familiar with these awesome images of planets that we can take, the planets in our own solar system. So this is a amazing image of Jupiter taken by the Hubble Space Telescope. I know some of you all are also taking pictures of Jupiter right now. It's a great time to take pictures of Jupiter. We can really see all this detail in the surface. We can see weather patterns on Jupiter, on these other worlds. We can watch these weather patterns change over time. And it's really been remarkable all the great images of planets that we have been able to take in our own solar system. So these are some of the real images of planets in our solar system that we have taken, all 8 planets. Sorry, Pluto. These are, but you can see, each of these planets, it's a whole different world. Each planet is unique and different from each other. And by taking pictures of these planets, we can really study their characteristics in detail. They're not just a dot. They have different compositions. They have different chemistries. Some of them have surfaces. Some of them may not have surfaces. And even one of these is hospitable, to life like us. So we really want to understand, what worlds are out there beyond the ones in our own solar system, beyond just the eight that we can take these really detailed pictures of. And I just want to mention the reason why we can take these really awesome pictures is that we can fly spacecraft to all of these planets. We can just travel to them, get up right up close, and take these really high definition, really detailed pictures. But we really can't do that for exoplanets. There's no way that we know of currently. There's no technology for us to travel to other star systems and take these awesome pictures. So, what can we do with the current telescopes we have to take pictures of other planets? If you follow astronomy news and you follow news about exoplanets, so that's planets orbiting other stars, you might have seen images like this. This is a press release image for Kepler 69c, is one of these planets that was discovered indirectly. And they kind of created this artist conception of what this planet could be like. But this is just an artist conception. We actually have no idea about any of these things. We don't know if this planet has clouds. We don't know if it's blue colored. We don't know what's in its atmosphere. We don't even know if it has an atmosphere. All we know for many of these planets is all we know is their size and their shape. And then the rest of this is kind of imagination, speculation. It's not pure speculation. We do understand physics. We understand, what kind of elements there exists in the universe, in our own galaxy. So there's not an infinite possibility of worlds, but the number of possible worlds out there, is quite large and varied. And the reason why we don't have information about exactly what this planet looks like, what it has clouds and things like that, is that the majority of planets that you've heard about, the majority of planets that have been discovered through indirect means. And what indirect means is that we don't actually see the planet itself, we see the influence of the planet, in particular on its host star. So you've probably heard about the transit method if you've done any sort of maybe if you've done amateur astronomy. And transit method is just when the planet just happens from our line of sight to pass in front of the star and briefly occult the star and cause the star to slightly dim. And this, because the planet's in an orbit, it does this occulting periodically. So we see this periodic occultation of the star that results in, if we just look at this brightness of the star over time, we see that brightness drops in this very periodic way. And from that, we can infer that there's some sort of planetary body that's orbiting the star that just happens to be occulting the star periodically. And from the depth of that occultation, we can estimate the size of the planet. But that's all we know. We just know its size. Another way we could detect the presence of stars, detecting the presence of planets around stars, is to take a spectrum of the star. If you take a spectrum of the star, you'll see absorption lines from the star due to the gases that are in the star's atmosphere. And if there's a planet orbiting that star is because of the star is gravitationally pulling on the planet, but the planet is also gravitationally pulling on the star. So you'll see from Newton's third law, the star is also wobbling around because as the planet orbits, it's also going to tug the star just a little bit as it orbits. And because the star is wobbling, when it wobbles towards us, it's like it's blue shifted. And when it wobbles away from us, it's like it's redshifted. And because of that, these absorption lines that exist in a star's atmosphere, they get moved to a bluer wavelength of light, and then to a redder wavelength of light. And this wobbling back and forth of the lines in the star's atmosphere happen periodically. And again, allow us to infer that there has to be a planet that's causing the star to wobble in such a way. So the vast majority of planets have been discovered through one of these two methods, through either the transit method, where the planet occults the star and causes a dip in brightness, or the radial velocity method, where the planet causes the star to wobble, and we measure the Doppler effect due to this wobbling of the star. So how about taking pictures of planets directly? So it turns out imaging planets is very hard. So just to give you an analogy, for the easiest planets that we can image to date, imaging planets is like trying to watch a firefly circle a street light this was written for an American audience, from several kilometers away. So just to give you a sense for the brightness ratio, the difference in brightness between an exoplanet and its host star, just how different that is, and also give you a sense for the angular separation. So like if you are viewing it from several, say, kilometers away, and you're trying to see a firefly circle a streetlight, that's the kind of angular scale that you're trying to perceive with our telescopes. So it gives you a sense for both how hard it is, because this firefly from such a far distance away will be completely swamped by the glare of that street light. It makes it really difficult to see that firefly. But we can image planets, and that's why I'm here to talk to you about that today. So here's our first image of an exoplanetary system. There are 4 planets in this system. As you probably know, we are not very creative at giving star names. So this is the star HR 8799 is the 8,799 star in this catalog. And there are 4 planets orbiting this star, and we creatively named the 4 planets B, C, D, and E. So that's just how we name planets in astronomy. So there's 4 planets orbiting the system, and you can see and then the star is kind of at the center of this image. What you're seeing here is not like you're not seeing like stellar flares or things like that. What you're seeing here, in addition to the 4 planets, is you're just seeing the diffracted starlight that is going through our telescope, and we try our best in image processing to remove that diffracted starlight, but we don't do a perfect job. And what you're seeing here is the remnants of the image processing of us trying to remove the diffracted starlight in our image. So the star is at the center, and we try to basically block it out, but it's not perfect, and that's kind of all the ripply stuff that you see in the image beyond the 4 dots. And I'd like just to point out, the planets look like, we have many pixels around each planet, but these are essentially dots. We don't have the spatial resolution in our images to resolve the planets. We don't see their surfaces. We just see a single point of light that represents like the combined emission from their entire surface summed together. So we're not able to resolve the surface of the planets. We're just able to see them and see them distinctly from the bright glare of the host star. So how do we do this? How do we make this image that you see here? So that's what I'll talk about next. So I drew this cartoon a while back for how do we take a picture of a planet. So our goal is to image kind of Jupiter-like planets. Let's see if I can get this laser pointer. Jupiter-like planets around other stars. That's kind of for the technology we currently have that we're currently capable of. We can only image kind of these Jupiter-like planets, these pretty massive planets around other stars. But still, we like to do that to try to find a bunch of these kind of planets. To do that, we generally use the biggest telescopes that we have, and the biggest telescopes we have are the ones on the ground. But because they're on the ground, the light of the planet and the star goes through the Earth's atmosphere, and the Earth's atmosphere, because there's atmospheric turbulence, distorts the images of the star and the planet. So what we have to do is basically use something called adaptive optics, and this idea of adaptive optics is basically giving your telescope a prescription that cancels out the turbulence, the blurring due to the turbulence from the atmosphere. And this prescription is one that you have to change very quickly. The turbulence in the atmosphere changes about every millisecond. So you basically have to apply a new prescription to your telescope every millisecond. So I know, like for me, I go to the optometrist once per year when I remember. But here, you have to go to the optometrist once every millisecond to get a new prescription to correct for the blur of atmospheric turbulence. Once we can correct for the blur of atmospheric turbulence, we have to use some sort of starlight suppression technology, often called a coronagraph, to block out the glare of the star before we're able to then take a picture of this exoplanet that orbits this other star. So I'll just give you a sense for why all these components are necessary. So here is an image of a star that we took without adaptive optics. So this is a bright star taken with the Gemini South telescope. This is an 8-meter telescope in Chile, and that's our impressive image of the star that you see there. It's a giant blob. This is because atmospheric turbulence basically blurs out this image of the star and creates what you're seeing here. So every frame, this is like a little animation. Every frame is about 1 second apart, and you're seeing how the star kind of completely changes in brightness and shape and everything every second. So you can see how badly atmospheric turbulence affects our images. But once we decide to turn on adaptive optics, this is what you see. So we go from this giant fuzzy blob into this nice crisp image of a star. So you can see how the image of the star gets a lot cleaned up, the light gets a lot more concentrated, and we get a lot more stable of an image of the star once we turn on adaptive optics. And maybe for some of you, since you been doing lots of amateur astronomy and looking at astronomical images, you'll also see that there's actually a second point source in the image right there. That's actually this. So it turns out this is actually a binary star system. And this star, the second star, is about 10 times fainter than the primary star. So we have two stars actually in this image. Previously, without adaptive optics, we would have no idea that that second star existed. That star would be completely hidden under the glare of the first star and blurred out by adaptive optics or atmospheric turbulence. So you can see the importance of adaptive optics and this is just for a binary star that's about 10 times fainter than the primary star. For a planet, we're talking about millions to billions times fainter than the star. So this is if we can't see binary stars, we have no hope for planets. This is why adaptive optics is necessary for us to image these planets. Let's see, advanced slide, please. Okay. The next thing we have to do is to block out the glare of the star. So here on the left, I've shown a simulation of a telescope system with perfect adaptive optics, saying that we've perfectly corrected the atmospheric turbulence. There's basically, let's say it's the telescopes in space, there is no atmospheric turbulence. And what I've simulated here is an image of a star and a planet without using any sort of way to block out the glare of the star. Without this thing we call a coronagraph. And all you see here, like there is a planet in this simulation, in this image that I've simulated, but there's no way that you can tell that it's there because the diffraction rings due to the starlight interfering constructively and destructively interfering with itself, basically, and that basically overwhelm any signal of a planet. And this is this kind of the diffractive nature of light is inherent to the quantum mechanics of light, right? Because light is also a wave-like phenomena, it will constructively and destructively interfere, and because of its fundamental nature, it will produce these kind of diffractive rings that would completely hide, again, any signal of a planet that we could see. So we have to basically put special optics called coronagraphs to basically suppress the glare of the star, suppress the ability of light to interfere with itself at places that we care about detecting planets, so that basically there's no light when light interferes with itself, it doesn't produce ripples at the locations where we want to see planets. So with the combination of both adaptive optics, you could remove atmospheric turbulence, plus using something called like a coronagraph to block out the glare of the star, we can actually see planets. And I've just kind of told you that chronographs are just kind of this mythical piece of optic that we can use. It's hard to show because chronographs are requires very precise optical alignment, and it's very hard to kind of have a real life demonstration of a coronagraph. But the closest thing that we have is if you ever have gone and seen a total solar eclipse. So I don't know how many of you have seen total solar eclipses. I highly recommend it. If you haven't, to go check one out. Solar eclipses are when the moon passes right in front of the star, right in front of our star, the sun, perfectly, so that it blocks out the glare of our own star. And this is a very fortunate circumstance for us to happen on Earth, that it just happens that the projected angular size of both the moon and the sun in our skies is about the same size as the moon could perfectly block out the sun when it eclipses the sun. So here's a very crappy cell phone camera a movie that I took of a total solar eclipse from last year when it happened here in the United States. So you can see this was the glare of the star, and then when our moon passed in front of our sun, you can see when it aligns perfectly that all that glare of the star gets completely suppressed and removed. And that's basically a chronograph off and a chronograph on is the difference that you're seeing here. And again, if you guys pay very close attention to this image, you'll see that once the chronograph turns on, when the moon perfectly blocks out the glare of our own sun, you'll see that there's a planet that appears. This, I believe, is Venus that was just happened to be here, and then but before the solar eclipse, you can see that it's really hard to see Venus, and then once we are in totality, suddenly you can see Venus bright and nice and clear. So again, this is a demonstration of how we can actually detect planets by suppressing the glare of their stars. Okay, so I'm gonna then now talk to you about a few planetary systems that I've personally been involved in discovering and studying. One of them is this planet called 51 Eridani B, or 51 Eri B. So the star is named 51 Eri. Again, here's an image of the system. We've blocked out the star with a chronograph. We try to suppress the glare of the star. What you're seeing here is kind of this residual starlight that we couldn't perfectly subtract off. And then 51 Eri B is the planet right here. So this is a planet that orbits its star just beyond the orbit of Saturn around our own sun. So it gives you a sense for the scale of this planetary system. This planet was discovered by the Gemini South Telescope in Chile. So this is a 8-meter diameter telescope. Is located at Cerro Pachón, elevation about 2,700 meters. So it's not the highest telescope in the world. Some telescopes we go to, you have to use supplemental oxygen. This is fortunately actually not one of them. You can actually go up there and there's not really any problems with altitude or things like that. This is a project I did a lot of work on when I was a graduate student. So yeah, here's an image of the Gemini South primary mirror. So this is the 8-meter mirror. This is a photo I took, and here's some of my colleagues. You can see here, you get a sense of scale. You can see kind of how big they are compared to the size of the telescope. And this is quite a behemoth. I tried moving the telescope. I wouldn't recommend it. The telescope is on motors. You don't need grad students anymore to move these telescopes around. It's a little bit too hard for us to move. One of the cool things that we've done is with the Gemini South Telescope with our instrument, we built what's called an imaging spectrograph. So in addition to, so we don't just get images at one filter or one wavelength. We get images at many different wavelengths simultaneously. And by getting images at many different wavelengths simultaneously, we can basically get a spectrum. Every pixel in our image also contains a spectrum. So what you're seeing here is an animation where we're stepping through all the different wavelengths we're observing at. And you can see the wavelengths down here. It's about 1.5 to about 1.8 microns. So this is firmly in the near infrared. So this is beyond visible light. These are kind of the wavelengths they use. Maybe if you see some nature documentaries and they show like nighttime shots with like night vision kind of things, they often shoot in these kind of near infrared wavelengths. These near infrared wavelengths are interesting to us because you can see here 51 Eri B is only bright for very few wavelengths, and almost all the other wavelengths is very faint. And if you measure the brightness of this planet as a function of wavelengths, you'll see that at many wavelengths it's faint, it peaks up in brightness, and it comes back down again. And the reason why it's really faint at many of these wavelengths is because there's water and methane in this planet's atmosphere. Again, this is a gas giant planet, a planet about 2 times the mass of Jupiter. So this is not water and methane in a planet like Earth, right? This is water and methane in a planet like Jupiter that we expect kind of to have. But nevertheless, we can measure these chemical constituents of this planet's atmosphere and kind of study, what are the chemical building blocks of these planets. Okay. Okay, and then the next planetary system I want to show you about, we've imaged using the Keck observatories, especially the Keck 2 telescope. It's this telescope here on the right. It's a 10-meter diameter telescope. It's located on Mauna Kea, on the Big Island in Hawaii. Um, and it's quite high up. It's about 4,000 meters up in from sea level. You do generally need supplemental oxygen when you're up there and trying to use, but generally, oh wait, it's actually that telescope. You actually generally we generally observe actually from the base, from the base of the mountain or remotely. We don't generally go up there just because of how physically demanding it is. And nowadays, a lot of stuff is computerized and and can be operated remotely, so we don't have to be physically at the telescope when we're operating, which is actually quite useful sometimes when it's very physically taxing like this one. This was the telescope that was used to discover the 4 planets that I first showed you around the HR 8799 system. So I already showed the 4 planets B, C, D, and E. And you also see these arrows, right? These are the arrows telling you this is the direction of orbital motion for these planets. And the nice thing for us is that by having we've been able to study the system for over a decade now, and because of that, we've been able to kind of take images of this planet system over time, and through that, we're able to actually make a time-lapse movie of these 4 planets orbiting the star. So this is I believe a 12-year time lapse of the 4 planets orbiting HR 8799. So you can see all 4 planets moving in this very counterclockwise motion around its star. You can see the movement is very slow. These planets are at very wide separations. The closest planet is about 15 astronomical units away from its star. This is beyond the orbit of Saturn already. So we're talking about planets that are well within in the outer regions of its planetary system. But nevertheless, we can actually watch these planets move. And this is when I first made this movie, it was like it was pretty mind-blowing even to myself. Um, like very rarely do we get to see kind of Kepler's laws in action, right? Johannes Kepler defined these laws of planetary motion about how planets move in ellipses around their stars. And within our own solar system, because we're embedded in our own solar system and moving alongside the rest of the planets, we don't really get to see that in action. We kind of see planets in the sky, but we don't really have that kind of visceral feeling that we're all orbiting the star. But here, because we can actually see a planetary system from top down, we can actually watch these 4 planets orbit the star together, which I thought pretty fun. And by watching these planets move in this orbit, we can actually trace out their orbits. So this is some work I did where we actually, based on their orbital motions, we trace out what are the possible orbits that are consistent with their orbital motions and try to analyze the dynamical history of the system. And the way we can do that is because we know how these planets are moving forward in time, but because we know the laws of physics, we know this is all this gravity, and we understand gravity very well, we can actually use its current positions and its current velocities and our understanding of physics and rewind the system backwards in time. So this is some work I did where we actually rewinded these systems in time. So we're actually moving, instead of moving counterclockwise around the star, we're moving clockwise around the star. So you can see these four planets kind of, this is in simulation, orbiting backwards as a function of time. You can see we're going back to 400, 500 years in the past. And we're using this to understand, what kind of dynamical interactions did the system undergo. And one of the things that we know is that the system, so we are here, we're testing a bunch of different orbital solutions. So there's many different sets of possible orbits that are consistent with the data. And our question is, what is the actual real underlying orbit? And what you just saw there, maybe on the right, is one of these sets of orbits become dynamically unstable. The planets interact strongly with each other and start ejecting each other from the system. We know that this can't be the case, right? We know that the system can't have evolved from a chaotic state and then naturally become somehow perfectly kind of calm. We know that, in the past, it likely needs to have stayed calm in order for the future and for present day for us to see it still in a calm state. So this allows us to actually exclude possible orbits that are not consistent, or possible dynamical histories that are not consistent, that are consistent with the data, but can't actually physically be true, because it will cause those kind of histories will cause the whole system to undergo kind of these large scattering events that cause the system to kind of fall apart. And we know how far back to rewind. So right now you can see on the animation on the left, we're rewinding about 3,000 years back in the past. In my analysis, I've rewinded all of these orbits about 40 million years back in the past. And why 40 million years? Because that's actually the age of the system. The system is about 40 million years old. So we know that the system had to have been stable. These planets have to have been orbiting each other in a nice, calm, and peaceful fashion for the last 40 million years. So a system where we could only go back 1,000 years in time and the whole system is disrupted, we know it's not a real solution. Whereas a system where we can keep going back in time for thousands, tens of thousands of years is a system that could be the possible dynamical history of the system that we study today. And give you a sense for how long ago 40 million years it is. 40 million years is pretty short on astronomical timescales. I really like this plot. This is a plot of Earth's geological history, in particular with when the dinosaurs came on Earth. So the dinosaurs were around on Earth about 230 million years ago to about 65 million years ago before they went extinct. So this system, which is only 40 million years old, formed after the dinosaurs. So these plants were born after the dinosaurs had already finished walking on Earth and had gone extinct. To give you a sense for just how young the system is, at least even in the history of the Earth, this is a very young system that we're studying. All right, and then here's just a nice zoo of a bunch of different planets that we have been able to detect to date. So just to you can see here they're all pictured around their host stars. Their host stars, we've usually done some sort of image processing to try to subtract off the glare of the stars. And the best way to identify planets in images is to look for the white arrow. The universe does not always provide white arrows for us, but your local friendly astronomers usually provide you nice little white arrows to tell you where to look to kind of see these faint exoplanets, even in the residual glare of the host stars that we try our best to remove, but we can't perfectly remove. All these systems that you see here, these are generally all very young, very massive, and generally all imaged in the near infrared. So these are kind of all planets between the mass of Jupiter to about 10 times the mass of Jupiter. They all orbit their stars beyond 3 astronomical units, and generally beyond the orbit of Jupiter and Saturn even. And they're all very young. These are all systems formed within in the last billion years. These are many of them formed within the last 100 million years. Many of them formed after the dinosaurs had gone extinct. This is where the kinds of planets we're imaging to date are kind of the extremes. They're the most massive, the youngest, the furthest away planets that we can access. But we want to get to more typical planets. We want to get to planets that are more like the planets in our own solar system. And in particular, we want to eventually image terrestrial planets. We want to be able to get to the point where we can actually look at terrestrial planets around other stars and see, what is their nature. If we look at the terrestrial planets in our own solar system, Mercury, Venus, Earth, and Mars, they all are drastically different. Each of these worlds, even though they're terrestrial planets, is completely different from each other. You have bare rocks, you have a runaway greenhouse effect, you have something that's just in the Goldilocks zone where life could evolve. You could have something that's mostly barren but still has ices and evidence from maybe in the past it could have liquid water. So we've had a very diverse set of worlds, and we want to know what's out there, what's out there beyond our own solar system. This next slide is the only kind of big slide on the only technical slide I'm going to show you. This is a plot that we use ourselves in kind of understanding the landscape of direct imaging, and I'm just going to slowly guide you through it. So on the y-axis, here on this axis, this is the flux ratio to the host star. So this is how much fainter of an object with respect to the host star that we can detect. Here, these points in orange and red, in red in particular, this is the sensitivity of our current instruments in the infrared that we've been detecting exoplanets with. We're generally imaging planets that are about 100,000 to 1,000,000 times fainter than their host stars. That's the kind of regime we're able to do. On the x-axis, this is angular separation. This is how far away they are from the host stars. Again, we're generally imaging planets about half to 1 arcsecond from their host star. And for folks that don't have a sense for 1 arcsecond, if you hold out your arm at arm's length and imagine at the tip of your arm a single bacteria cell that's residing at the tip of your finger because you haven't washed your hands yet, that bacteria subtends at the tip of your arm, subtends a angular size about 1 arcsecond. So eventually what we'd like to do is to image Earth-like planets around other stars. Let me see if I get my laser pointer back. So we would like to image Earth-like planets around other stars. And to do that, we need to image planets that are about 10 billion times fainter than its star at an angular separation about 1/10 of an arcsecond from its star. So this is a whole different regime than the current regime of planets that we're currently studying. What we've been working on right now is to basically demonstrate a level of demonstrate technology in this kind of intermediate regime, so that if we can get here, then if we build some specialized telescopes, we have a chance of getting down here to imaging kind of Earth-like planets around other sun-like stars. And this kind of demonstrating this level of technology that we're hoping to do is being done by a mission called the Nancy Grace Roman Space Telescope. Someone made a sidewalk art kind of drawing of the space telescope. So it's about the same size as Hubble. We're talking about a 2 meter diameter primary mirror and this is like the telescope enclosure that you're seeing here, and in the back the instruments will be held over here. The Nancy Grace Roman Space Telescope is actually, hopefully, if all things go smoothly, will be launched in the near future, somewhere between 2026 and 2027. And it is going to do 2 things. One, it's going to do this wide field infrared survey of the sky. And you can see here this logo of the Nancy Grace Roman Space Telescope. This is the detector footprint of its wide field survey. You can see it has a bunch of different detectors all overlaid together, so it can get a huge patch of the sky all at once. We're not going to talk about this at all. We're going to talk about this little thing in the O. The little thing in the O is the second instrument that's going to be on the Nancy Grace Roman Space Telescope. It's the coronagraph instrument. It's our instrument that we're going to use to demonstrate new technology that can hopefully get us to imaging habitable worlds in the future. And this coronagraph is going to demonstrate a bunch of new key technologies that will hopefully enable exo-Earth imaging Earth around other stars. We're going to be flying in space for the first time these very large deformable mirrors. These are the mirrors that you saw in the cartoon where I talked about going to the optometrist every millisecond to correct for atmospheric turbulence. In space, there's no atmospheric turbulence, right? But in space, the telescope optics are still warping because it's just like you're getting different amounts of solar radiation as a function of time. There's just like slight vibrations and perturbations in the telescope. The optics warp. And the fact that the optics warp over time will actually degrade our ability to see exoplanets. So we actually need to be able to measure and correct for any warps in the optics on the course of minutes, hours, many hours kind of timescales. And we have to correct it to a precision of about 10 picometers. If you've never heard of a picometer before, 10 picometers is approximately 1/10 of the size of a hydrogen atom. So we're talking about extremely, extremely tight tolerances that we're trying to do. And the reason why we have to do this is that we are going to use these deformable mirrors with this extremely, extremely precise resolution to basically optically cancel starlight and basically dig what we call digging a dark hole around the star. So we're basically going to optically cancel starlight to basically cause only destructive interference of starlight in an annulus around the star in which we're able to actually search for planets. And these planets that we're going to see are extremely faint. These planets that we're going to see are going to be, we're talking about planets comparable to the brightness of like the faintest galaxies that we're imaging. So in order to do spectroscopy of these planets in the future, in order to look for things like signs of oxygen, signs of water in these planets' atmospheres, we basically have to make every photon we collect count. So we're also flying these new sensors that are able to count basically each individual photon of the planet that arrives onto our telescope. Basically use that to basically maximize as much information as we can in order to look for and characterize any exoplanets we see. We're also flying a bunch of new optical masks. I'm not going to go into much detail about these, but these are the things that actually block and cancel the glare of the stars to first order. And you can see some of these cool designs that people have come up with to kind of do even more sophisticated canceling of starlight. And one of the things I'll be in charge of is working on blocking out the glare of figuring out how to do data processing and removing all the residual glare of the star in our data to create nice, pretty pictures of potentially exoplanets that Roman will detect. So that's kind of the goal for Roman, and the broader picture goal is that maybe in the future, if this technology has demonstrated to be true in a future observatory like this planned Habitable Worlds Observatory concept that NASA has been pioneering, to look for signs of habitability. So this is a spectrum of the Earth, and this is actually a real spectrum of the Earth, and it goes from a large range of wavelengths. This goes from the ultraviolet into the visible, into the near infrared, out into the mid infrared, and out into further into the mid infrared. And what you see here, like all of these kind of features in the Earth's spectrum, these are all due to various molecules in the Earth's atmosphere, things like water, ozone, oxygen, carbon dioxide. And our goal is to, eventually look for signs of habitability, we want to eventually be able to get to a point where we can actually take these spectra, look at these various constituents in the planet's atmosphere, and try to assess whether these planets could be habitable. This is certainly challenging, and it's going to be no one will tell you this will be easy, but it's something I think that will be very interesting to do. One of the coolest things that we could possibly see in our spectra is what we call the red edge. The red edge is basically the fact that we could maybe see the evidence of photosynthesis on another planet. We know photosynthesis is the primary way on Earth that a lot of life generates energy, harvests energy from the sun, and turns it into usable energy it can do for other processes. And to do that, all these photosynthetic life on Earth have basically are very good at absorbing light shortwards of essentially red. So any green light, bluer than green. It's hard to say. Basically, any shorter wavelength light gets absorbed by the plants, whereas longer wavelength light, because it's not as useful, gets reflected. And you can imagine that if you have a whole surface covered by plants that are photosynthesizing, covered by algae, covered by trees, something like that, that you could actually see in the reflectance of the exoplanet itself, that it kind of like suddenly turns up in reflectance at these wavelengths that maybe photosynthesis turns up. So this is one kind of thing we think about of like how we could maybe directly detect life and look for biosignatures on other worlds. Like I said, this is all very, let's say we're in the very early stages now. We're even just trying to get us to the point where we can get to the technology to the point we can actually make these measurements. The interpretation of measurements, such as spectra of another world, whether this combination of molecules is is one that's definitive, that tells us this world is habitable, or maybe it could be a false positive. All of this stuff, I think, is still, actively being researched, and there's no clear answer yet. But I think once we have developed the technology, this will be a very exciting question to ask. So I'm just going to end with this really awesome picture that I like from Voyager 1. So this is one of the spacecraft that has flown furthest from our own solar system. And as it was passing by, I think Saturn, it actually turned around and took a picture of Earth. So this is its image of an Earth-like planet around a sun-like star. And you can see here all of this stuff. This is the glare of the star that's basically diffracting into Voyager 1's optics and making it a little bit more difficult to see that pale blue dot. You can imagine, Voyager 1 is still only at the distance of Saturn. Earth is still pretty well separated from the sun, and the sun's radiation is not super blocking in the way. But for a Earth-like planet orbiting another star, that star is going to be much, much closer to us, much, much closer to the Earth than this, and then in this image, and we're going to have to deal with all of this glare of the star to subtract it off to look for a pale blue dot like this one. Okay, I think that's all I have. I'm happy to take any questions and stick around and talk about any of this stuff. Thanks.
Well, thank you for that, Jason. That was fascinating. Before we go on to questions, can we thank Jason for his talk? Thank you.
Thank you. Thank you.
Yeah, if you're on Zoom, can you put your name or your question in the chat there? And if you're on YouTube, if you have a question, put it in the comments there as well. So we have a few. I have just one question, Jason. So the Roman telescope is obviously quite a lot smaller than the 10-meter Keck on the ground and things like that. And I would have thought that the resolution is down to the large size of the aperture more than anything else. So presumably the space telescopes are still going to be quite restricted. What they can do.
That's a very great question. So yes, the Roman telescope will be quite smaller than these 10-meter telescopes on the ground. The one advantage is that the fundamental resolution limit of a telescope goes as wavelengths over size of the telescope. So on the ground, we're looking at even with bigger telescopes, we are generally looking only in the near infrared at these longer wavelengths. But the Roman Space Telescope will be able to look at visible light. So visible light is about factor 2, factor 2, is that right? Factor 2 to 3 times shorter in wavelengths than the ground-based wavelengths that we're using in the ground-based telescope. So the resolution ends up being slightly worse, but actually not too different because of the fact that we get able to go do shorter wavelengths of light.
Okay, thank you. Ian, you had a question? Do you want to ask it?
Yes, that system you showed us with 4 planets. Obviously, the chronograph technology currently means it looks like you can't go any closer than about 20 AU.
That's right.
But could that system have planets closer in, and would you see the perturbations on the 4 that you can see?
That's a great question. There certainly could be more planets closer in. There's been a few studies where we try to understand, dynamically, could you put more planets in? Where could you put them? Could they be dynamically stable? And like you said, because there's still a lot of room, there's about 15 astronomical units of room within our detection limits that you could put planets in. Actually, maybe 12 astronomical units. Yes, basically, yeah, there could be planets in there. We're not really sensitive to those planets. Even the other indirect techniques, they're not very effective at detecting planets around this star. So we really are in the dark about whether there are more planets closer in.
Okay, thank you.
Mm-hmm.
Tim, you had a question? Do you want to ask that?
Yeah, thank you very much. That was really fascinating. Apologies if you already explained this, but I wasn't quite sure. So how are you dating these solar systems?
Yeah, that's an excellent question. I just asserted that to you, so you have to believe me. So, we are dating these systems by studying their stars very carefully. So, young stars, as they're evolving, look different than stars on the main sequence. Our billion-year-old sun-like stars look a little bit different than young stars, which are still kind of in their a little bit more active phase. They have a slightly different spectral features. So there's a variety of different tools that people use to date stars. I would say dating stars is difficult, and dating any one star is actually quite hard because there are a lot of different ways that you could create the kind of spectral signatures that you see in a star. The one advantage is that stars are often born in clusters or groups. You have a big cloud of gas, basically, and you can imagine that cloud of gas collapses into many different stars. And a lot of the planets that we have imaged reside in these what we call moving groups or associations. And what we can do is basically try to apply our stellar dating techniques on all the stars in a group or association. And each star may not have great constraints, but when you combine all the different constraints together, you can end up with actually a pretty precise measurement of the age of the group. And you kind of assume that the dispersion of ages in the group is pretty small, usually only a few million years, and that most of the stars in a group have about the same age. So that's a really good question. It's very subtle and it's not very easy to do.
Okay, thank you. Clive, are you able to ask your question? Have you got a microphone?
Can you hear me?
Yes, we can hear you.
Okay. Well, basically, when you back computing the planetary orbits, I assume there's an assumption in there that they're all orbiting in either the same plane or pretty much the same plane. Or the
Yeah, that's a great question. Yes, we made an assumption that they were. I think the ones that I showed you, we forced them to be exactly in the same orbital plane. We've also relaxed that assumption and looked for planets that are like ever so slightly inclined. But when the planets are too mutually inclined with each other, that just induces dynamical instability, and those orbital solutions are basically impossible to find stable solutions when you have orbits that are not within a few degrees of basically in the same plane.
Okay, thank you. Thank you.
We have Wolfram Cosmos here. He hasn't got a microphone, so I'll read it out. When imaging planets around red dwarf stars, are these more difficult or easier to observe compared to terrestrial planets around sun-like stars? I.e., does the lower brightness of the star compensate enough for the much closer orbits?
That's a great question. Sounds like someone knows quite a bit about direct imaging, and indeed, when we're talking about trying to image planets in the habitable zones of other stars, the habitable zones of red dwarf stars are much closer in because they're much cooler. So to get the same amount of radiation to be warm enough to have liquid water, you need to be much closer to that star, and when your planet is much closer to the star, you can reflect more starlight, basically. And it turns out that being closer to a star is observationally more favorable. So imaging terrestrial planets in the habitable zones of red dwarf stars is generally considered easier than imaging Earth-like planets in the habitable zones of sun-like stars, just because being closer in and brighter compensates for the fact that you do have to be much closer to the star. And in fact, people are building telescopes on the ground. You heard about the extremely large telescopes. One of the ideas is to go after planets in the habitable zones of red dwarf stars. Those 30 to 40 meter telescopes on the ground won't have the sensitivity to see Earth-like planets. Won't have the sensitivity to see Earth-like planets in the habitable zones around sun-like stars in reflected light. That won't be possible for the ground-based telescopes, but they will be able, if everything goes well, asterisk, these we're pioneering new technologies that we haven't. It's not quite there yet. This is an active area of research. If everything goes well, our goal is to image with the ground-based telescopes to look and try to image planets in the habitable zones around red dwarf stars in reflected light. So yes, it is easier to image planets around red dwarf stars generally, we think, in reflected light. It is also easier in thermal emission. The one challenge is right now, sorry, I'm going on digression. One challenge right now is that we're only sensitive to gas giant planets, and red dwarf stars, because they're much less massive, have a more difficult time forming red giants, gas giant planets. So even though we are sensitive to gas giant planets around red dwarf stars, we haven't really found any because there's not the frequency of gas giants around red dwarf stars, which is a lot lower.
Okay, thank you. Jim, do you want to ask your question?
Yeah, thanks for the talk. I noticed that you said that the sensors are sensitive to a single photon. And I was just wondering that without the Earth's atmosphere, you're going to have much more issues with cosmic rays
Yes.
causing effects that are going to
Yes.
trigger the sensors.
Yes.
Is that a concern at all, or can that be filtered out effectively?
Yeah, this is a great question. It can basically be filtered out effectively with these single photon counting detectors. Our exposure times are so short that basically in a single image, you expect either 0 or at most 1 event. And if that 1 event is a cosmic ray, it should have it's very different signature on the image than a single photon, basically. Because
So what are your exposure times?
We're talking. I don't want to say the wrong answer right now, but we're talking second, or we're talking probably around a second kind of time scales.
Wow.
Yeah.
Thank
But
you.
I don't want to say the wrong answer right now because I don't remember it exactly off the top of my head. This is different than what I normally do. This is different than what we normally have done from the ground because these planets in space are so faint. The number of photons that actually arrive at the telescope from these planets is very few per second, basically.
So do you take multiple exposures then in effect?
Yes, we have to take many exposures, and we'll like do image processing all of them and then combine them together to get enough photons. Yes.
Oh, great. Thank you very much.
Okay, we have just one more question that's from YouTube. Dylan on YouTube asks, do you think red edge would be definitive proof for life, or is there enough doubt that it could be caused by something else?
I think that's a great question. I think of many of the things that we think we can plausibly detect, red edge is probably the most definitive of anything. I think coming up with a combination of other spectral or geological features that can produce the red edge certainly could be plausible, but and I'm not fully aware of all the research on all the various false positives that could blend in with the red edge, but I think it is certainly, would be more definitive than just saying detecting oxygen or water or something like that. I think there's a lot of abiotic ways to produce things like oxygen and water, whereas trying to produce a feature that looks like the red edge, I think the number of false positives is lower.
I'll briefly ask Nigel's question. He's just popped in there. In an ideal world, what would be the specification of a space telescope necessary to see the actual planetary disk?
If you want to spatially resolve the surfaces of planets, I think there's 2 ways. One is you need at least if you want to do like an Earth-like planet, I think you need tens of kilometers a size of a telescope. At that size, you basically can't build a single telescope. You will need to build an optical array of telescopes and interfere that array interferometrically to basically have the spatial resolution to resolve the surface of, say, a terrestrial planet. I think even a Jupiter, you require like probably 10-kilometer baseline essentially to get that kind of spatial resolution. Yeah, it's just in a sense, we're talking about 10-meter telescopes right now, so we're talking about a huge leap in angular resolution. Another way that has been proposed, which would be really difficult, is to essentially use the sun as a gravitational lens to magnify an image. If you know exactly a system, if you know a system has a planet that you want to spatially resolve, you could fly a spacecraft to the edges of our solar system and use the sun as a gravitational lens to basically magnify that particular planetary system and try to actually resolve the surface of a planet. But you have to be extremely precise. You have to know exactly where you want to look, when you want to look, and basically plan your spacecraft trajectory with all that in mind. And that's kind of like a theoretical thought experiment at this point. Actually building a mission for doing that would be, there's many engineering challenges that would come with that, basically.
One day, maybe, yes.
Yes.
Okay, well, thank you, Jason, for that, and thank you for answering all the questions. Can we thank Jason again for that excellent talk?
Well, thanks for having me. Enjoyed all your questions, and thanks for all the interest.
While that has been happening, we've been running our remote telescope in Spain. I thought I'd just share that with you since we can briefly see it.
Yeah, let's do it.
There we go. So that's a live view of our telescope, and it's currently imaging in hydrogen alpha IC 1848. That's what it's doing live in Spain at the moment. So not
Wow, that's great.
we do exoplanets occasionally, but not tonight. So
Right. So this is a single exposure that we're seeing here?
that's hydrogen alpha, a 300-second exposure. Yeah. And it's
Wow, this is
it'll take
amazing.
a bunch of those. Yeah.
It's great. And what's the size of the telescope?
It's a 0.3 meter telescope. So telescope, yeah.
Pretty substantial.
And this is what we've got lined up tonight. It's automated. It's doing a bunch of variable stars. And that's the main imaging target. We're keeping an eye on T Corona Borealis, as everyone else is, to see when it pops, and a comet in there as well. So that's what we're up to tonight in Spain.
Very cool. Very cool. And the weather is good, it looks like.
Yeah, it is. Yeah, it is. We've had a few problems with it, but it's all working.
Mhm.
Yeah. Okay, well, that's it from us tonight. I hope we'll see you again online. And thank you very much again, Jason. That was an excellent talk, and a good crowd as well on YouTube and in the society. So it's obviously a topic that interests people, and it was really good. So good night, everyone. We'll see you again.
Thank you. Good night.